Good Friday, everyone. Happy Thanksgiving Day weekend, and welcome to Science Friday number 4. This week, we're going to talk about something near and dear to my heart, which is space travel. Now, I grew up in the late 50s and early 60s watching the Mercury missions and then the Gemini missions and then the Apollo missions. I was 12 years old and I was enthralled. I watched the whole week in July 1969 when men first walked on the moon. That interest I parlayed later into a career as a physicist, and as most of you know, I taught at a university for 25 years. And not only did I work for NASA a couple of times under some contracts, but I taught astronomy and astrophysics. Those were two of my regular courses that I taught in my career as a senior lecturer. But I got to tell you right off the bat, I'm here to kill your buzz. Because if you're one of these folks that's all wound up about, this stuff that's going around right now about we're going to be able to send humans to Mars within a decade, I'm here to tell you that that's not going to happen. I would bet on it. And I think science is on my side, and I think that I'll be able to explain it to you in a convincing and compelling manner over the course of the next 10 minutes or so. Now, I know these guys, Elon Musk and Richard Branson, are tripping over each other right now, trying to be the first to figure out a way to send a crewed rocket to Mars and be the first to send human beings there. And there's all this talk about how this is going to happen by 2030, and that's not going to happen. And I'm going to tell you why. And there's basically 6 reasons why, and I want to go through those 6 reasons with you right now. The first problem with sending humans into space is that the way that we get you into space right now is with a chemical rocket. They're either fueled with liquids or solid chemicals, and you have to have a lot of it to get things even in low Earth orbit. To get something to escape Earth's gravitational bonds, which is what you have to do to get something to the moon or to Mars or someplace else in the solar system, you have to have a really big rocket. It took the Saturn V to get us just to the moon, which is pretty close, because you have to achieve a speed of 24,500 miles per hour, or else anything you send up eventually falls back to Earth. Now, there's a way around that called a space elevator, and some complexities involved in that. Maybe we'll discuss one of those on down the road. Then once you get it there, the fuel is mostly spent, so you're kind of coasting the rest of the journey to get wherever you're going. When we went to the moon, most of that was a coast. So the rocket gets you up to a speed above 24,500 miles per hour. You get to some speed above that, and then your speed doesn't change a lot until the very end of your journey when you're decelerating, or when you're coming back, when you're accelerating and come back the other way. Now, the second thing you're going to run into are problems with radiation in space. And radiation in space comes in 2 flavors. There are so-called cosmic rays, which are basically high-energy particles that zip around everywhere in the universe. And there's cosmic radiation, which in our solar system principally comes from the sun. It's basically parts of the electromagnetic spectrum, X-rays, gamma rays, things like that are produced in the sun. The sun also, during solar storms, solar flares and prominences and sunspots, produces particles that are a lot like cosmic rays except lower energy, and they zip through space as well. Now, living on Earth, we have an atmosphere that protects us and a magnetic sphere that surrounds that atmosphere, or magnetic field, I should say, a magnetosphere that protects us. You go out in outer space, you get beyond the atmosphere, you get beyond the Earth's magnetosphere, you don't have that protection anymore. So what are you going to do? Well, you either have to surround your spacecraft with a jacket of lead or gold or a big jacket of water, something that's going to be able to intercept most of that radiation. And all those things are heavy. They make your spacecraft very massive and even harder to get out of Earth's gravity well into space. Now, you could build it in orbit, but you still got to get all that stuff up there somehow. That's a problem that nobody's figured out yet. The way that they do it in science fiction, if you look at the Starship Enterprise here, that big dish below the saucer section is called a deflector array, and what that's supposed to do is create an artificial magnetic field that steers all of those particles away from you and all that radiation away from you. But that doesn't get invented for another couple of centuries, so we're a little out of luck there. Another problem with crewed missions that go into outer space, as opposed to robots, is that greater than 80% of the payload is going to be life support for the human beings. You've got to have food, you got to have water, you have to have a breathable atmosphere, you've got to have all this radiation shielding that I just talked about. You've got to have some source of gravity. And we're going to talk about that in just a second. All of this stuff ends up weighing a lot, has a lot of mass. It takes a lot of energy to get it out of Earth's gravity well, and it takes a lot of energy to propel it through space, which means that you don't have very much payload left for things like instrumentation, tools, things like that. Now, you send a robot, which we've very successfully done on many missions over the last 25 years. Huge return on investment. Robots don't care how long it takes to get there. They don't need food. They don't need water. They don't need a breathable atmosphere. They don't need as much radiation shielding. You still have to shield the electronics a little bit, but not as much as you do for human occupants, for biological organisms. Huge bang on the buck for robots. I'm a big advocate of sending robots instead of humans with the current state of technology. Now, let's say you figure all that stuff out. Going to the moon or Mars, you don't have to worry about relativity very much. But if we were to go beyond our solar system and start to explore other star systems, you'd have to start worrying about relativistic effects. And I don't have time to talk about those in detail here. I may do that. I may do a Science Friday just on the twin paradox at some time. But I suggest that you look up something called the twin paradox. The twin paradox is real. And what it means is that if you figure out a way to travel very fast and you go very far in space, because space and time are not separate entities, they're two parts of the same thing, something known as space-time. When you take these long journeys, when you come back, your clocks are not aligned anymore. And if you were to take a journey to even the nearest star system, a little over 4 light years away, at let's say 20-30% of the speed of light, when you got back, everybody that you knew and loved on Earth would have been dead a long time. And that's a very inconvenient feature of space travel. And unless you can figure out a way to build artificial wormholes or something to shorten that distance, that's a constraint imposed by the physics of the universe on space travel for humans. Now, what this means is that all this is very expensive, and we just don't have the technology to address any of this right now. In order to travel very far in space, you need a whole bunch of things. You need to create an atmosphere somehow. You need water, you need food, you need a magnetosphere or some other shielding against cosmic radiation and cosmic rays. And you need to generate some source of artificial gravity because humans don't do very well in extended periods of microgravity. Now, how would you create gravity? Well, the way they do it in most science fiction shows is they just have an artificial gravitational field. And I'm here to tell you that unless we invent an awful lot of new physics, we're not likely to get artificial gravity. That's centuries in the future to figure something like that out. It just has to do with the way that gravity works and how gravity is created in nature. So you're going to have to create gravity but through rotation. So in a lot of science fiction movies, these spacecraft have these big rotating sections. Well, that's all well and good, but what the science fiction shows don't get right is the size that rotating section has to be in order to create anywhere close to the gravity that you experience close to the Earth's surface, which we call 1G. In order to do that in space with one of these rotating drums, the thing has to be humongous. It really has to be big. And even then, if you make the thing miles across, it's still hard to get up to 1G. You got to make the thing truly enormous in order to get 1G of gravity without some very disorienting effects. You get vertigo. There's a Coriolis force that's going to cause havoc whenever you, like if you toss a ball up in the air, you try to pour a glass of water. There would be all these incredibly disorienting effects unless you were able to build something really, really big. So basically what you need to travel in space if you're a human being, if you're going to spend very much time out there, is you need to figure out a way to build a small asteroid, something, a little bit smaller than the moon maybe, hollow it out on the inside, spin it up. You could, the surface of the asteroid would prevent the shielding that you need from radiation. You could create a biosphere on the inside of it. If you spun it up, you could create gravity without too many disorienting effects. Bolt a bunch of rockets to it, and you could make the thing go really fast through space. That's basically what you're going to have to do, and that's expensive and still depends on technology that hasn't been invented yet. But that's what you're looking at. So the problem with space is that things aren't close. Things are very, very far apart. And even in our solar system, where it is, it's technically possible to send things on these long journeys to get someplace. Like the quickest we could get to Mars is a 6-month one-way journey. That's a long time. So you talk about 6 months to get there, whatever time you spend, 6 months back, you're gone a year, 2 years. And Mars and Earth don't maintain the same relationship to each other. They move at different speeds around the sun. So the journey's much likely to be way longer than that, because you have to plot your journey so that Earth and Mars are relatively close to each other, or else you have to have really big rockets and use a lot of energy to get there. It's very complex to figure out a low energy way to send a payload from Earth to any place else in the solar system and get it back. So there you go. I'm sorry I killed your buzz about travel in space, but those are the problems. Those are real problems, and right now we don't have a way to deal with those problems. Now, we can fix all that stuff. Humans have come a long way just in the last couple of centuries when it comes to technology. And I'm sure that we will eventually figure out a way to solve all these problems. But you're not going to solve these problems by spending a lot of money building chemical rockets to go to Mars. In my view, that is a waste of money. You would be much better off taking that money and going into a laboratory here on Earth somewhere and seeing if you can figure out, build a superconducting super collider. See if you can figure out a way to create a fifth fundamental force at a certain energy regime. See if you can figure out a way to create artificial gravity at some specific energy regime. See if you can create elements at a certain energy regime that don't exist in our periodic chart. Those are the kind of things that are going to help you figure out a way to get very far, very fast in space. Anyway, I'm running out of time. Again, please feel free to ask any questions or leave any comments. BC. Cheers.